Wait, can you go back to the last one?
Mhm. Now, the first step in the process on the previous page told us to draw a diagram. The last two questions I didn't bother because, well, I struggle drawing a sphere, and a cube isn't really much better for me, but I also didn't think you needed me to draw it in order to know what they look like. Okay? But in the case of number 3, it's talking about a point moving along the curve such that the x-coordinate is increasing by 4 units per second. All right, so it might be a good idea to draw the curve. I'll give it a y-intercept of 9. X-intercept of 3, and just rough it out. Doesn't have to be perfect, we just want to get a decent visual on it.
We just use our calculators.
Yeah. Graphing parabolas by intercept, so it's pretty quick though. So x-intercept you get just by taking a look at the h value in this case. There's no k value, so it's right on the x-axis. And for y-intercept, you just replace the x with a 0 and simplify. I just thought that there was some like interesting phenomenon at work where the day that we're doing something in calculus, I'm teaching that concept for the first time in Algebra 1. Like it always works out like that. Like whatever you need to understand in calculus, I'm always teaching that in a level or 2 levels below that course. It's really kind of cool. Anyway, they tell us that the x-coordinate is increasing by 4 units per second. All right, so that's telling me, I could just make a note here. The rate of change of x, they didn't give me units for that, per unit of time. All right, so it's going to be 4, but they didn't give me the units, so let's just call them units. Per second. The key is here that it's increasing. So the 4 is going to be positive. If they said decreasing, then we would make the 4 negative. All right, so that's an important piece. All right, and that piece of information applies to both parts A and B. Now, it says at the moment that x is equal to 1, I don't need to rewrite that because it's pretty straightforward. It's asking how fast is the y-coordinate changing. So I want to know what dy dt is equal to. Now here, I don't need to invent a formula. I don't need to grab a geometry formula because they gave me an equation that relates x and y. I just need an equation that relates dx dt and dy dt. All right? So I'm going to take the derivative of this. Dy dt is going to be equal to what? I also need the derivative of the thing on the inside. Because x could be a function of time. Dx dt. All right. And so take a look at your related rates equation, because the derivative equation is also known as a related rates equation in this context, because I have a rate on the left side, I have a rate on the right side. The equal sign relates the one to the other. All right. So I'm going to take a look at that and just make sure I have everything I need. I'm looking for dy dt. They gave me an x. They also gave me a dx dt. So I have all the ingredients to just plug and chug at this point. All right. So dy dt is equal to 2 times 1 minus 3 times 4 that's going to give us negative 16. All right, my units there, same units as x, they're both linear. So units per second. All right, this one might be a little bit easier to visualize based on the curve that we have. You didn't actually need the curve in order to do the work. I think you need the curve in order to understand what the work means. So you have a point that's moving along this parabola. At one point it was up here, then it moved down to here. It's going in this direction. So these are all the points that exist. But we're getting a little bit of a snapshot when x is equal to 1, but this is the point in motion. You do this on GeoGebra with a slider and you can see it a little bit better. But what's happening is the x value is moving in the positive direction, right? You're moving further and further away from the y-axis as you travel along the curve. But in terms of y, it's pretty clear that it's moving downward along the graph, right? So that justifies the negative part of my dy dx. It's going downhill. It's just a question of, well, does that 16 make sense in this context? Well, that's a lot harder to determine. I mean, I suppose it would make more sense if you were on that roller coaster. But unless you could actually physically experience what's going on, I don't know that you can necessarily relate to the 16 part of it, right? But at least the negative part is justified, right? But that's telling us that at this moment in time, for every 4 units traveled per second in the x direction, we're going to lose 16 units in the y direction. Right. And with a parabolic relationship, you don't expect a lockstep relationship. You don't expect it to be 4 for x and 4 for y. You expect it to be some other number.
For word problems, don't you have to have like a 1-sentence explanation to like say how it relates to the?
That's the answer in context.
Yeah, no, I know, I understand.
Yeah.
But are you supposed to have it?
Generally, yeah.
Okay.
Yeah. So I've just been saying it.
Okay.
Yeah.
But like for points, we have to write it.
Yeah, you'd write it, yeah. So for B, at the moment x equals 1, how fast is the point's distance away from the origin changing? That could be a little bit more interesting. So I'll just do a rough sketch. Oh, too rough. I'm talking about this distance. All right. Now, any distance in space is Pythagorean in nature. So let me just bring that bad boy in. Extreme close-up. All right, so here's a little teensy tiny right triangle in there. I'm going to label one side x. Vertical side I call y. And the hypotenuse I'm going to call r for hypotenuse. That's that whole radius connection from trig. So we have a relationship, x squared plus y squared is equal to r squared. Now that distance, that's the hypotenuse, we're calling that r. All right, because another fun fact is every distance in space is the radius of some circle. Right? Actually, every length is the radius of some circle. When you get further and further in calculus, you'll see that everything becomes a circular relationship. It's kind of hard to think of it that way because we look at things on the micro level, but once you expand outward from there, everything is circular. Right? And it's kind of a strange thing to think about. But I have a relationship. That's cool. It looks like I probably have too much information in my equation, but I can take the derivative, 2x times what? dx dt plus 2y dy dt equals 2r times dr dt. It's kind of like learning a foreign language. You know, you know enough to say times dx dt times dy dt times dr dt. You may not quite yet understand why. Right? You're just basically learning the alphabet in French, I guess, something like that. All right. So I have an x. I have a dx dt. They told us that in the first part. Because it's still at x equals 1, so the same circumstances are in play. I have a y, a dy dt. I mean, that's y, in case you were wondering.
What's why?
No, I was talking to someone else. All right, so I just need some information. I got my dy dt, I got that from the last problem, negative 16. The only thing I'm missing really is a y, but I can figure that out, and an r. All right, so let me get my dy dt. Just for clarity's sake. All right, so we had our derivative, our related rates equation, and we got to a point where we're ready to substitute. So the x and the 4, they were both given to us. The negative 16 we figured out from the first problem. The y and the the y and the r, we need to figure out in order to determine what dr dt is equal to. And that's all coming from the right triangle. So if we can evaluate that, we'll be in good shape. All right, so the key to this whole thing is knowing that the equation of the curve is y equals x minus 3 squared. All right, because if you know that the value of x is equal to 1, I'll just kind of tuck it in right there. Then every coordinate on a curve is x comma y, but the y is particular to the function. All right, so in this case, we could figure out that the y value would have to be 4 because we replace the x value with 1 and simplify. So that'll give us a 4, 1 comma 4, which tells us the y value is equal to 4. All right, so that's the part I rushed through yesterday, and I didn't want to leave people hanging. All right, so if I just kind of take a closer look at that right triangle with dimensions of 1 and 4, the hypotenuse by Pythagorean theorem, 1 squared plus 4 squared, 1 plus 16 is 17, the square root of which is the square root of 17. So that's where all that magic was happening. All right. So that r value, which we recall in the hypotenuse, would then be the square root of 17. All right. So we knew that the y value is going to be 4 because we just solved for that, and we're looking for dr dt. All right. Now, I noticed that there's a coefficient of 2 across the board, so we might as well kill those. You can actually multiply it out, but eventually you're going to have to divide out of 2 when you simplify. So why not take care of it right now? So we're looking at 4 plus negative 64 is equal to root 17 dr dt. So 4 plus negative 64 is negative 60. So dr dt is going to be equal to negative 60 over root 17. We just have to state the units. All right. Now in this case, the units are units, so that's nice. Units per unit of time, which in this case was seconds.
Yeah.
So units per second. All right. If we were talking about an area, it would be square units. If we were talking about a volume, it would be cubic units. All right. So you just have to kind of understand the nature of the situation. All right. So this one's definitely beefier, part A and B together, because really, if you think about it, the question could very easily be just part B, in which case you'd have to do all of part A anyway. Okay, so if that's the case, then that makes this particular question, number 3, like orders more challenging than 1 and 2, right? Because even though you were given an equation, you had to do a lot more with it, right? But the good news is it's Pythagorean in nature. All right, Pythagorean relationships, when it comes to related rates, are so commonplace that you can kind of rely on some of these steps as prior knowledge. All right, so you'll get to a point where you won't be finding out derivatives as much as you'll just be remembering it from the last 10 times you did it. All right, so that, the familiarity part of it, in this case, won't breed contempt. So that's good news. All right, in the next problem, a ladder 10 feet long rests against a vertical wall. Classic ladder against a wall problem, you do it in every math class. If the bottom of the ladder slides away, this is the little twist on this problem. From the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Right, so diagram, I think, in this case makes sense. Let's draw a wall. This is my wall. That is a poor quality L, so I'm going to revisit that. I'm going to draw a ground, or at least attempt to. In math class, we always assume that a wall and the ground form a right angle. All right, we always make that assumption because things get infinitely more complicated if you don't. All right, so the only way they wouldn't be forming a right angle is if you were told otherwise. All right, when there's construction involved, when people are actually building buildings, the ideal situation is to have a right angle. All right, that's how you actually support the structure. All right. Not always possible, because if you're building on the side of a cliff, that could be an issue, right? So in that case, you'd have your struts kind of going into the cliff at an angle, but not the case here. It's just a wall, right? And there's a ladder leaning against it. And some poor schmo standing on this ladder. If you'd like to draw the schmo, you're welcome to. The schmo is none too happy about the situation. No, cool people don't have hair.
What about facial hair?
Oh, facial hair, totally. I mean, that much is obvious. Let's get it in here. I might have to go to the palette. If you are wondering if this has ever happened to me, you need not wonder.
Yeah, it's just like a thinly veiled version of you just telling a story.
No, it's a legit beard, of course.
Excellent.
It's a TED Talk.
Everything I say is a TED Talk.
Everything I say. That'd be a really good thing.
It is really good.
I think he needs a hat.
Like a please change.
Yeah, can you draw a hat?
Oh, I gotta put my.
How about a shirt and pants?
He needs glasses.
Put a little flash.
Oh, definitely need. Oh, yeah, the flash thing. How to Kill a Class Period by Period 7. There we go. And a blue. It's.
Is that hair?
No, it's my hat.
Oh.
Yeah, put a little brim going off to the left. It's like a helmet.
No, it's not my hat.
What type of hat is that?
It's like you're facing front.
It's like a
on,
peak.
so you kind of look
Yeah. Although when you draw your poor schmo looking like this, you would think that merely a ladder sliding down would be no challenge for this individual. All sorts of powers available to him. So anyway, oh, that's a pretty sick
It
drawing.
looks like he's riding it almost.
Yeah,
Surf.
just riding the wave. No big deal. Look at this guy.
No danger. He's out there.
Yeah, I could totally do that. Except that's not what happened. It really hurt. It was painful. But not as painful as the time that I was cutting Tyvek. Tyvek is the wrapping that you put around the side of a house before you put the siding on. So when you're constructing a house or any other kind of structure, you put the studs, and then you bang in the plywood, and then you put the wrapping around it. That's the Tyvek. And you cut that with a razor knife, like a Stanley knife. Yeah, so I was cutting it.
Place your leg.
Right through. And I was wearing some pretty heavy jeans. That didn't stop the blade though. It was quite painful. Yeah. Same day as that too. Sucked. So anyway, the ladder's 10 feet long. bottom is sliding away at a rate of 1 foot per second. So we'll define our variables. This distance we'll call x. All right? So if it's moving at a rate of change, so that horizontal distance is defined as x, that's telling us that dx dt, the rate of change of x, would have to be 1 foot per second. One thing you got to be careful about is direction is important, all right? Because this ladder is sliding away from the wall, but it's only positive because of the way I drew the picture. All right, it's going in the positive direction. All right, if I drew it so that the wall was on the right-hand side and the ladder was leaning against it, then the base of the ladder would be sliding in the negative direction. So it does depend on how you draw your picture.
So it's like XY plane kind of thing, where like.
Exactly. All right, so what that means is that your calculus needs to coincide with your diagram. And if it doesn't, you're technically incorrect. All right, and this whole class is all about technicalities. So anyway, how fast is the top of the ladder sliding down the wall? Okay, so let's define the vertical distance as y. The ladder is going in the downward direction. Bless you. In which case, dy dt is completely unknown. That's what we're looking for. And they told us the length of the ladder overall is 10 feet. I don't want to draw it on a ladder because the diagram looks so great. But what we're looking at is a Pythagorean relationship. All right? I'll just kind of tuck a little r in here so that we could say that x squared plus y squared is equal to r squared. If we differentiate this, we're going to get 2x times dx dt plus 2y times dy dt equals 2r times dr dt. All right. Same result as the previous problem. So there's really no new work to be done here. All right, so that's good news. We could even kill the 2's right off the bat. And we'll be looking at x dx dt plus y dy dt equals r dr dt. All right. So we have some information. All right, they're saying how fast is the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall. All right, so when x is equal to 6. So I could say 6 times 1, because dx dt is given as 1, plus, I need my y, I don't have it yet. I'm looking for dy dt. R I don't know. Oh, actually R I do know is 10. Dr dt, actually let me just leave parentheses there. I don't know dr dt, but we could figure it out pretty easily. All right. So actually let's start with that part, because that's not going to require any computation. Dr dt is referencing the rate of change of the length of the ladder. Which would be what? Nothing. It's going to be 0. The ladder's length is not changing. All right. Now, there are extension ladders that do change in length. They didn't say anything about that in the problem, so you can't make that assumption. And you don't want to make that assumption. All right? You wouldn't be able to solve for a clean number. Right? You would actually solve for one rate in terms of another rate. And that there's value in that also, but in this case, it's not within the parameters of the problem, so it's not necessary. All right. Now, in terms of the y value, that's easy enough because again, we're living in the world of right triangle relationships. Not even trig, just Pythagorean theorem. I know the base is 6, the hypotenuse is 10. What's my missing side? Very popular Pythagorean triple, 8. That's the basis of it, though. It's the 3, 4, 5 right triangle just scaled up.
Yeah.
So you have the right idea. All right. So I know the y is going to be 8. So 6 plus 8 dy dt is equal to 0, and therefore dy dt is going to be equal to negative 6 over 8, so negative 3 over 4 units.
Meters per second. No, right? It's feet.
Feet, yeah. Feet per second. All right, so now, I mean, the question doesn't ask us to interpret this in any way, although you should always try to do that. With the idea of the volume changing in a sphere and the size changing in a cube, it's kind of hard to conceptualize that sort of thing. But a ladder sliding down a wall. Now it's starting 6 feet up, and it's decreasing in height at a rate of 3/4 of a foot, which would be, what, 9 inches every second? So the question would be, that I would ask you, is this person in danger of injuring themselves? Well, I guess there's always a danger. When you wake up in the morning, you're in danger of injuring yourself. I actually know a person who broke her ankle getting out of bed. That happened because her foot fell asleep. She got up,
Oh, and just like
didn't realize she was on an angle, stood, put all her weight on it, and cracked.
Oh.
Yeah. So just getting out of bed is enough to put you in jeopardy. That's why denial is part of the human nature.
Shouldn't the ladder's speed be increasing as it goes down, though?
Right, yeah. So we're kind of living in a vacuum here because we're neglecting the effect of gravity. So that's the thing, because we're assuming that there's a constant rate of change in x, which would lead to a constant rate of change of y. But gravity does have a pull here, so it should actually be speeding up. So there's that component of it.
Wait, so how is it negative? How is it like a negative number? How is speed negative?
So negative velocity indicates direction.
So it's velocity.
Right,
So velocity can be negative, speed can't be negative.
right.
So it's velocity that we're getting?
We're getting velocity up. So actually, in all these cases, we're getting velocity. It's speed with the positive or negative sign. The negative sign indicates the direction. All right, so we're going downhill in this case. All right, so is this person in any danger if these conditions remain the same? No, it seems to be going down at a pretty slow rate. All right, so the question I would ask as a follow-up, how did I get hurt? I don't know. Like, I was on this ladder, and it's kind of like I almost hit a guardrail when I was driving my car. It was in Mayapack back in the day, and I was going down. It was Union Valley Road. I was going down. I don't even know what part. It's like the first mile of it. There's a sharp turn, and as I was going down, the road was slick. It was winter, so it was pretty icy, and I lost control of the car. I wasn't even going fast, but I lost control of the car, and then I had that slow sideways. You have time to ponder what the consequences are of your actions, like the meaning of life kind of thing. Like, all right, yeah, so there's the guardrail. I'm gonna hit that in 15 to 20 seconds. I can't do anything about it. It's gonna happen. Do I just stay here? Do I get out? Like, what do I do? I don't know. I just watched it all happen. And then, right at the last second, the car caught a dry spot, and I was able to regain control. I was like, ooh, dodged a bullet there. I did not hear. It was slowly going down. I think it was like paralysis by analysis. I'm on this ladder being like, it's going down. I don't.
There's nothing I can do.
Nothing I can do. And then, boom. Foot caught under the ladder. It was very painful.
Yeah, I was gonna say, did you get caught under or hit your head on the ladder?
No, I've managed to avoid head injury, but what is it? Metatarsal? Is that the right word for it? Yeah, one of those cracked. Did not feel good. Yeah. I was in quite the pickle. But anyway. So, that was a rough day for me. But I was wearing a cool hat. I didn't have that t-shirt though. This sick, like, CW Flash t-shirt. But anyway, you know, you can evaluate some situations. You can't evaluate all of them. All right, so the case of the sphere, this problem, can you conceptualize this? No. But these you can potentially reason your way through. All right, so, you know, obviously the emphasis is going to be on problems more like number 4, because if I'm going to ask you to analyze a situation, I'm going to give you situations that you have at least a hope of analyzing.